Well, the final topic of this chapter is sensors based on luminescence quenching. Okay, the quenching means the process whereby emission from an excited molecule is decreased by energy transfer to another molecule. That molecule is called the quencher. Okay, let's develop the quenching equation. Okay, when a molecule absorbs light, the electron is goes up to the excited state. Yeah? So it's represented here as this asterisk, the symbol. Okay. So the absorption rate, yeah, from the rate theory, we can write this rate is proportional to the concentration change of the excited the molecule, the molecules with time. Okay, because here the sign is positive because absorption means the production of these excited molecules. Okay, so we can write this absorption rate, and it is proportional to, okay, it is a reactant, okay, this molecule. Ka is a proportional constant. Ka means absorption, and then these excited molecules undergoes several fate. The first fate is the emission, okay, by fluorescence or phosphorescence. Okay, this is exactly the opposite process of absorption. Okay, now it emits this one, the electromagnetic radiation, but the only difference is that the frequency of the emitted light. Okay, so this emission rate is proportional to this one, that this excited molecules concentration, but we put negative sign. Why? Because by emission, this excited state, the number of molecules decreases, so we write this way. Okay, and then in short, it is proportional to this number of the concentration of excited molecules, and proportional constant is Ke. Okay, and then another the fate of excited molecule is deactivation. Okay, that's a simple deactivation. Yeah, this excited molecule come go back to the original this one, the molecule, and generate the heat. Yeah? The heat depends on the energy difference between these two molecules. Okay, so this rate is also, we put a negative sign because this deactivation process also is the process that decreases these excited molecules. Okay, and the proportional constant is Kd. Another mechanism is quenching, yeah, which is our interest now. Quenching is that what you need a third body. Okay, the Q, in this case Q, this is quencher. Okay, this excited state react with the quencher, and energy is transferred from this M star to Q. As a result, M and Q star are produced. Okay, this rate is also proportional to this excited molecules concentration. Okay, but when we write the equation, this one rate no, this is proportional to the product of concentrations of this M star and Q. Okay, although expression is given by this one, and then using the concentrations we can write it this way. Okay, KQ is a proportional constant. All right, and what else? So there are one, two, three, four. Basically, four the processes when the molecules absorb light. Yeah. Okay. The fate once it is excited, it goes to excited state, and then uh, the fate of these excited molecules are emission, deactivation, and quenching. Okay, and the rate of appearance of this one, okay, excited state molecule is proportional to the original concentration of this molecule. This is absorption. Okay, so only absorption makes the appearance of SAR. The other 1 to 3 processes, that's a process that disappear these excited molecules. Okay, so the rate of disappearance is given by the sum of these three processes. Okay, there's at steady state. The steady state means that if you keep irradiating the molecule with light, okay, and then absorption and disappearance the rates becomes equal, okay, and then apparently there is no change, okay. This is kind of equilibrium, okay, but in actuality, mm, that means the rate of appearance equals the rate of disappearance, okay. That's the steady state. In the case we can equate this rate of appearance with this rate of disappearance, okay. This is simple mathematics. Here, yeah, the quantum yield, quantum yield we often meet, yeah, in chemistry that deals with the light, okay. Quantum yield for a photochemical process is that it's a fraction of absorbed photon, this is a photon pH, producing a desired result, okay. For example, in photosynthesis, light is absorbed by light harvesting molecules called chlorophyll, okay, and then chlorophyll absorbs the light energy, and then the energy is transferred to the reaction center, and then electrons are excited, okay, in the reaction center. In the case, quantum yield is the ratio of number of electrons per absorbed photons, okay. So actually, the quantum yield is a general term for a photochemical process, the fraction of absorbed photon producing a desired result. Okay, so if molecules absorb, for example, 100 photons and only 30 molecules are excited, then what is the quantum yield? Zero point 0.3. Okay, all right, yeah, like that. So here is the mathematical expression for quantum yield. Now, quantum yield in this case is expressed phi 0. Okay, quantum yield for emission from this one. Okay, excited molecules. But here, since we monitor these, you know, different processes, so we can monitor the emission, okay, emitted light, with the spectrophotometer, okay. So for the emission from excited molecules, the quantum yield is defined by this one: photons emitted per second divided by photons absorbed per second, okay. In this case, quantum yield is expressed, you know, as this equation. So this is a emission rate divided by absorption rate, and this one, okay. Very simple. And we keep on going. All right. What is the quantum yield at steady state? Okay, which is the quencher is no is not present. Okay, the quencher concentration is 0. Okay, that's the quantum yield. Okay, phi 0. Okay, in the absence of quencher, and quantum yield is expressed by this one. Okay, and in this case, this one q is 0, and then it is very simple. It's simply expressed by this equation. All right, very easy to understand. But what if you add the quencher molecules, okay, and then this term q term is survive, okay. It is one. This is called phi sub q, okay. In luminescence quenching experiment, we measure emission in the presence and in the absence of quencher, okay. That's the usual practice in luminescence quenching experiment, okay. So here, if we take the ratio of phi 0 with respect to phi q, yeah, and then we get this equation. from this equation, you just simply take a ratio, right? And it is simplified as 1 plus parenthesis kq over ke plus kd and multiplied by the quencher concentration. Yeah, this is called Stern-Volmer equation. This is very widely used, yeah, in quencher experiment. All right. Yeah. So if you plot, okay. Oh, and then how do we know the this one, no? Phi 0 and phi q? This can be measured by measuring the current, okay, intensity of luminescence. Okay, I0 is intensity without quencher, and IQ is intensity with quencher. Okay, and then we change quencher concentration from 0 to certain value, and then we measure this ratio, and then we can make a plot. And this is a simple linear plot. Okay, the y-intercept is 1 when q is 0, and this is a proportional, this is the what slope. Okay, so um, this is the result. Yeah, and then you may find that this Stern-Volmer equation really well applied, okay, in this quencher experiments. All right. And the final topic is a luminescence intracellular action sensor. Okay, using this luminescence, usually fluorescence, okay, we can measure the action concentration in the cell. Okay, how? It is very difficult. Okay, there is action probe. Yeah, is commercially available, but that action probe is extremely larger, yeah, compared to cell size. Okay, how do we do that? And there is a technique. Okay, and then you see O2, inside the cell, the O2 molecules are there, and O2 molecules are good quencher. Okay, it behaves as a good quencher for this very strongly fluorescing this molecule. Okay, this complex, this ruthenium complex is a complex to this DPP molecule. DPP here stands for 4,7-diphenyl 1,10 phenanthroline. Okay, yeah, this is very strongly fluorescing. Okay, and then in the presence of oxygen, this fluorescence intensity becomes decreasing. Okay, why? Okay, here, okay, let's see this one. This molecule is M. Okay, and then when it absorbs light, okay, and then the one electron from the ground state excited to the what, higher level, okay, like that. So at the ground state, these electrons are paired. Okay, that's a single state. But once it absorbs light and then becomes excited state, then electron spin has the same direction. That is triplet state. Okay, and then here you have oxygen. Okay, from the molecular orbital theory, oxygen have has two unpaired electron. Okay, unpaired electron. So that's why oxygen molecule is paramagnetic. Okay, not diamagnetic. Yeah? Paramagnetic. That means the oxygen molecule is attracted toward the what? The magnet. Okay, why? Two electrons on the highest energy level. Two electrons are residing on different orbital, okay, with the same spin. Okay, in this case, the author expressed as the spin, is spin down, to spin down. Maybe spin up, maybe okay, but here is spin down. Okay, and then this oxygen molecule behaves as a quencher. Okay, this one. So when this oxygen reacts with excited state of molecule M, and then energy is transferred. In other words, one of electron is transferred to the oxygen energy level. Okay, here, this is rather unstable, and then the electrons in upper level now moves here. Okay, to the ground state. Yeah. As a result, okay, this energy is transferred, not electron, to the oxygen molecule, and then the as a result, this molecule M now went back to go back to the original state. And what about the oxygen, the triplet state, and becomes a single state. Okay, and this is the single state energy level is slightly higher than this one, triplet state. Why? Because electrons are, you know, oppositely, direction is opposite. Okay, spin state is opposite. Up, one is up and one is down. Okay, yeah, you understand? The energy is transferred from excited state to the ground state oxygen molecule. Right? That's how this oxygen molecule behaves as a quencher. Hmm? All right. So inside the cell, um, so we can measure the fluorescence. In other words, the fluorescence is emitting from the cell, and you can detect from the outside the cell. But we need reference. That means that we need this light sensitizer. Okay, but the sensitizer should not be affected by the presence of oxygen. Okay, what are the molecules? Okay, here, but your our textbook does not exactly say about the molecule. But here, look at that. This one, this molecule, ruthenium complex, is definitely a good fluorescing uh, the molecule. Yeah, and it is very sensitive to the oxygen. But the another dye, it says green dye, but this one is red dye. This green dye, we don't know the what the exactly it is. Okay, but this green dye, it also generate fluorescence. Okay, but the this intensity does not depend on the action. Okay, okay, and then the next step is very simple. Okay, so you inject very small beads of several hundred nanometers beads coated with two dyes. This one, green dye and red dye. Yeah, you inject those beads into the cell, and two dyes emit fluorescence at different wavelengths. Yeah, this is very fortunate. This one, green dye, emits fluorescence at 525 nanometers, but this red dye, yeah, this one, it gives off the fluorescence at more than 600 nanometers. So they are well separated. But this one, green dye, is not affected by oxygen, but this one, red dye, is strongly affected by oxygen. Okay, green dye is not sensitive to oxygen. Okay, yeah, yeah. Emission intensity ratio. So you take the emission intensity ratio, this one and that one, and then you can relate this emission intensity ratio to the concentration inside the cell. All right. Here is the result from the textbook. Here, the left column is conditions, and right column is intracellular oxygen, the concentration in ppm. Air saturated buffer solution. Okay, the intracellular oxygen, you know, the concentration is 8.8 ppm. Why? Because you blow the air into the solution where the certain cells are there, and then cells. We can easily think that cells inside cells are maybe full of oxygen. Okay, so in this condition, intracellular oxygen concentration is high. In this case, highest. Cells, I'm sorry, yeah, air saturated buffer solution, yeah, this one. And the next one, yeah, next row means the cells. You put the cells in air saturated buffer, and then some oxygen in air saturated solution now enters the cells, right? And then inside cell, oxygen concentration increases. Okay, but not as not as big as this one, yeah? This air saturated buffer, okay, but its concentration increases to 7.9 ppm. Yeah, this is slightly lower, and cells in buffer 25 seconds after removing oxygen, okay, after removing oxygen for uh, 25 seconds after, okay, and then oxygen concentration decreases, okay, so the and then we measure 25 seconds after, it is 6.5 ppm. It slightly decreases, but if you measure the inside cell concentration after 120 seconds, okay, and then you you here you see big difference. The oxygen concentration inside cell is only less than 1.5 ppm. Why? Oxygen is removed, okay, oxygen is removed by the cell, okay, it is consumed, okay, and uh, here this one, this let's look at this figure again here, and when purged with oxygen here, okay, and then since this is very sensitive to oxygen, and then the fluorescence intensity quite low, and purged with air, and this is the pure oxygen. In this case, air contains about 20% of oxygen, and then oxygen concentration is lower than this one, and then fluorescence intensity increases, okay, and then when you purge solution with nitrogen, okay, and then the inside the cell the oxygen concentration becomes lowest, and then fluorescence intensity becomes higher, okay, yeah, so with you know, by taking this fluorescence spectrum, you can estimate the intracellular oxygen concentration. Okay, yeah. Okay, this is the end of chapter 18. Okay, I selected several homework problems, and then you solve these problems and then upload in the eCampus. Okay, yeah.